Yeah, hello everybody. Welcome to your last skill check for this course. This is the lecture 16 and 17 skill check covering the topic of multiple linear regression. So the scenario. Here, the performance of students who study introductory statistics varies in part due to individual differences. However, there may also be systematic differences, such as the proportion of classes a student attends, the proportion of questions asked or answered by a student, and the self-reported average proportion of time during which the student pays attention. So we're imagining that Dr. Sokwe, who teaches introductory statistics, randomly selects some of her students each year and keeps a record of their attendance and participation. At the end of each semester, she also asks each student to self-report the proportion of time they paid attention in class on average and records their final grade. So the following analysis is based on data collected from 120 students. So question one, here we're going to look at the scatter plots. This is the visualization component of the analysis. It's always the best thing to do first is to look at the data. And here what we're mainly looking for is to see whether it appears that each of these predictor variables is linearly associated with the response. And so here we have our three predictors: attendance, participation, and attention. Each is being plotted against the final grade. And so I think it should be pretty obvious for most of us that there are linear trends in these data clouds. But the one for participation is not very noticeable. So here we can say that attendance and attention, they both appear to be linearly associated with grade. For participation, the relationship looks linear, but the slope is approximately 0. So we can expect when we do this analysis, we may see that there is a significant association between attendance and grade, and between attention and grade, but perhaps not so significant in the case of participation. In any case, there's no reason to say that the trends in these data clouds are not linear, and therefore we can try all three predictors in our model. One thing to notice here before continuing is that the predictors are all expressed as percentages. So you can see here as we move along the horizontal axis, participation is expressed as a number between 0 and 100%. Attendance and attention are also expressed between 0 and 100%. And so that is important to remember because what it tells us is that a unit increase in any of these predictors corresponds to a 1% increase. That will be important when it comes time to interpret these slopes that we get when we do the analysis. So we'll keep that in mind. Now before continuing, I also want to show you something from a web page I found online. There's actually a site called QuantHub, and they have lots of different explanations for various aspects of statistics. Here I was looking at how to use scatter plots, and this is the scatter plot they showed. And now the reason I'm showing you this is I want to be sure you understand what your data will look like if the data was not linear, if there was no linear association between predictor and response. And so here in the top two plots, we can see examples where there's, in the first case, a positive linear association, and in the second, a negative linear association between a predictor and response. This is kind of what it would look like. In both of these cases, the relationship is quite strong because there's not very much scatter in those data clouds. Looking at the bottom, we can see two cases where the relationship is not linear. So in the first case, you can see the relationship here is sort of S-shaped. And in the second case, you can see the linear has a distinct curve. Sorry, the data cloud has a distinct curve in it. And so the point is, when you're looking at your predictor versus response, if that data cloud looks like either one of these, then there is no linear association. There is an association, but it's not linear. And because it's not linear, you cannot use the linear model. At least you can't use that one predictor in your linear model. And so this is the kind of thing we're making sure we don't see before proceeding with the analysis. Just to tie that back in, this was the attention versus grade, and you can see there's a distinct positive linear slope in that case. Although, of course, the scatter is much larger than what you see in these two examples. And so the linear association exists. It's not as strong as the linear association depicted in these two diagrams. But clearly, there's nothing like an S shape or a curve. And so we're okay here to assume that the relationship is a linear one, and we can therefore use attention in our analysis. And that was true for all three of the predictors. If you want to look more into QuantHub, then you can just click onto this link. So question 2 is about the F statistic. In this case, the F statistic for the omnibus test is 88.30, as you can see in the table. And so here we're going to look at how this statistic was calculated, what the null hypothesis is for the omnibus test, talk about whether we accept or reject, and what is the appropriate conclusion for the test. So we're going to draw a conclusion. And finally, we're going to talk about the coefficient of determination. So a lot going on here. Let's start with that F statistic. So one thing to note here, we have an analysis of variance table for the omnibus test alone. So this table isn't showing you any of the individual predictors. And so what is it we need to look at? To calculate the F statistic, we need to remember that the F statistic is a ratio of variances. And where do we find variance? We find them in the column that's called the mean sum of squares. The mean sum of squares is a measure of variance. And so here, we're going to look at the variance in the 120 final grades that is explained by the regression model. And so that's this number on top. And we're going to compare that to the variance due to individual differences. That's the number here below. So the F statistic, it's just a ratio of the variance in the original 120 measurements that's being explained by the regression model versus the variance that is left over that is attributed to individual differences. And so that ratio is 88.28, which rounds to 88.30. So that's an agreement with the Minitab output. Notice that this F statistic has 2 degrees of freedom. The first degree of freedom corresponds to the degree of freedom for the number on top, which you can see from the table is 3. That's the degrees of freedom associated with the regression. And the second degrees of freedom is that associated with the error, 116, as you can see from the table. So are we going to accept or reject? Well, what is the null hypothesis? The null hypothesis for the omnibus test is that none of the predictors are associated with the response. In other words, the null is that the population slopes for all 3 predictors is 0. We could write it like this. Are we going to accept or reject that null hypothesis? Well, we just need to look at the p-value. Here we can reject the null hypothesis because the p-value for the test is very small. So if you're conducting your test at, say, the 1% level of significance, the p-value is less than 1%, so we can safely reject the null hypothesis. And so that means we can conclude that at least one of the predictor variables is associated with the response. In other words, at least one of the population slopes is statistically non-zero. The important thing to remember about the omnibus test, it doesn't tell you which of those individual predictors is associated with the response. It just tells you that at least one of them is. That's why it's called an omnibus test. The last thing here, I think, in this question was to talk about the coefficient of determination. And so here we need to remember that the coefficient of determination compares the variation in the 120 final grades that is explained by the regression model to the total variation in those 120 final grades. And so it's just this ratio. And just let's remember that the sum of squares measures variation. The mean sum of squares measures variance. So here, calculating r squared, we get this ratio. It's approximately 70%. And so we can say that about 70% of the variation in the 120 final grades is explained by this regression model. So to put that in context, that's a very good percentage. That's telling us that the model will do a good job in making predictions about either the population mean final grade or an individual final grade. I'm just trying to say 70% is pretty darn good. Right, next question. Looks like we're going to fill in some missing values in our analysis of variance table. Notice that this table now includes rows for each individual predictor. So it still includes the row for the omnibus test, but now it's including the individual predictors. Right, this table shows both the omnibus test, which is the first row, and the tests for individual predictors. So starting with degrees of freedom, the regression degrees of freedom is just equal to the number of predictors in the model. So for regression, there's 3 predictors. The number here is going to be 3. The predictor degree of freedom, for each one of these individual predictors, it's 1 for each of them. And each of those, of course, adds up to 3. The total degrees of freedom is just the number of data points minus 1. So there was 120 observations. N minus 1 is 119. The error degrees of freedom is the number of observations minus the number of predictors minus 1. 120 minus 3 minus 1, that's 116. And we note that if you take the error degrees of freedom and you add to it the regression degrees of freedom, you get the total degrees of freedom. Next, we're looking at the it's the adjusted mean sum of squares, but I just call it the mean sum of squares, right? Mean sum of squares is a measure of variance. So how do we get those? The mean sum of squares is just the sum of squares divided by the corresponding degrees of freedom. And so, for example, if we want to get the mean sum of squares for regression, we take the sum of squares for regression and divide it by its corresponding degrees of freedom, which is 3, and we get this number, 9,949.1. This number. Likewise for all of the other mean sums of squares. So for example, if we're going to look at the error, where did this number come from? Well, that's just equal to the sum of squares for the error term divided by its degrees of freedom. So it's that 13,070. This number divided by the corresponding degrees of freedom, we get 112.7. And finally, the F statistic. So the F statistic is always a ratio of variances. The F statistic for each predictor compares the variance in the 120 final grades that is explained by that predictor to the variance due to individual differences. So if for attendance, for example, we have for attendance the variance associated with attendance is this 21,642.6. We're comparing that to the variance due to error, and that ratio is 192.04, which you can see here. We can do likewise for the other 2 individual predictor variables. Right, so what are we going to say about these 3 predictors? Well, we can see each of these F statistics has an associated p-value. The null hypothesis for each predictor is that it is not associated with the response. In other words, the null is that the population slope for that predictor is 0. So for example, for attendance, we would write the null hypothesis is that the population slope for attendance is 0. The alternative is always, for Minitab, it's the two-tailed alternative. That slope is not equal to 0. And so we can see that we're going to reject the null hypothesis for attendance because the p-value is so small. We're going to reject it for attention because the p-value is so small. For participation, not so much. The p-value is very large. So we can say that there is no significant association between participation and the final grade. Right. So this tells us then that we're going to build a model that only uses attendance and attention for our predictor variables. We're going to throw out participation because it has no significant association with the grade. Right, so just go back for a second. So one way to determine which of the predictor variables should be included in your model is to look at these p-values for the individual predictors. Another way to do it is to compare the r-squared adjusted. And so here, the r-squared is the proportion of variation in the 120 grades that is explained by the regression model. So here we have five different regression models that are different in terms of the predictors that are included. So the first model includes only x1 attendance. The second model includes only x3, that's attention. The third model includes x1 and x3. The fourth one includes x1 and 2. And the last model, the fifth model, includes all three of those predictors. So r-squared here, this first column shows you the proportion of variation in the 120 grades that is explained by each of these models. R-squared adjusted is the same proportion, but after adjusting for the number of predictors in the model. So this is the important concept, is that if you add predictors to your model, even if you're adding a predictor that has no association with the response, R-squared will always go up. R-squared adjusted takes into account the number of predictors in the model, and R-squared adjusted will only go up if the predictor you add is in fact associated with the response. And so you can kind of see that here. We're looking at R-squared adjusted to determine which is the best model, and we're picking the model with the largest R-squared adjusted. So what you'll notice is for R-squared, if you add, you can see here the model we're looking at in green contains attendance and attention. It contains x1 and 3, attendance and attention. If we add participation to the model, we're down here now, the model with all three of those predictors, you can see that R-squared actually went up a little bit, but only a little bit, and so it doesn't show up here. So if the top number is 69.50, the number down here might be 69.51, for example. We don't know for sure because Minitab didn't give us those decimal places, but it's certain that the R-squared for the model with all three of the predictors is a little bit bigger than the R-squared for the model with only the two. R-squared always increases, but if you look at R-squared adjusted, the model with two predictors is 69.0. The model with all three predictors is 68.8. It went down a little bit. And that's because R-squared adjusted accounts for the number of predictors that you put in the model. R-squared adjusted will increase only if the predictor you put in the model actually is associated with the response. So in this case, this predictor, this was participation. Participation had no association with the response, and therefore R-squared went down, right? So that's why we use R-squared adjusted. I should have said R-squared adjusted went down. That's why we use R-squared adjusted to pick the best model. Right, so the best model in this case is the one with the largest R-squared adjusted, and it's the model that contains attention and attendance as the predictor variables. Okay, question 5. Here we're going to do some inferences. We're going to make some inferences about these population slopes. So we're going to calculate confidence intervals. We're going to interpret those confidence intervals. And then we're also going to perform a hypothesis test. So before you do any of that, you have to know what the degrees of freedom is for your test statistic. And so something to remember is in the case of multiple linear regression, the model, in this case, it contains two predictors. And so the degrees of freedom for the distribution of the test statistic for making inferences about a population slope is the same. Okay, wait. So I just noticed this statement doesn't make any sense. So let me just correct that before I continue. It's true that the model in this case now contains only two predictors. We've chosen to get rid of the participation as a predictor because it didn't have any association with the response. But that doesn't really matter for what I'm trying to say here. All I'm trying to say here is that the degrees of freedom for the distribution of your test statistic for making inferences about a population slope, and when I say making inferences, I mean either constructing a confidence interval or performing a hypothesis test. That test statistic, it's a t-distribution, and that t-distribution has a degrees of freedom that is the same as the degrees of freedom for the error term in your analysis of variance table. So in other words, it's the number of observations minus the number of predictors in the model minus 1, in this case 120, minus 2 predictors minus 1, that's 117. So we can use that to approximate the critical value for a 95% confidence interval. In our table, we do not have 117, but we have 100, and we're going to use that as an approximation. We're looking at the two-tailed probability, or in other words, a 95% confidence interval. We're looking at 100 degrees of freedom, and so our critical value is 1.984. Right, so looking at the first predictor, attendance, the 95% confidence interval for the population slope, it's the point estimate, which is 0.5401, plus or minus the margin of error, which we calculate using the critical value, times the standard error for this population slope. And so we get this interval, as you can see. So how do we interpret this interval? Well, we can say that we are 95% confident that after accounting for attention, the population mean grade increases by between 0.46% and 0.62% for every 1% increase in attention. And since this interval doesn't contain zero, the association between attendance and grade is statistically significant. So we can do all the same thing for the second predictor, the attention. We start with the point estimate plus or minus the margin of error. The margin of error is calculated using the critical value times the standard error for this coefficient, and we get this interval. And so we can say we are 95% confident that after accounting for attendance, the population mean grade increases by between 0.18% and 0.42% for every 1% increase in attention. Since this interval does not contain zero, the association between attention and grade is statistically significant. Right, so now turning to the hypothesis test, we're going to use the same critical value. We're going to use plus or minus 1.984 to set up our decision rule. And so here, the null hypothesis for each of these predictors is that its population slope is zero, meaning that the predictor is not associated with the response. The alternative hypothesis is that that population slope for that predictor is not equal to zero. And so what are we looking at? Well, we have our t-statistics, and we have the associated p-values. In the first case, where does that t-statistic come from? For attendance, it's just equal to the estimate of the slope minus what that slope would be if the null was true, divided by the standard error for that estimated slope. We get a value that is bigger than our critical value for our 5% test. And so we're going to reject the null. And that's consistent with the fact that our p-value is very small. Likewise, for attention, we have our point estimate for the slope for attention minus what that slope would be if the null was true, divided by the standard error for that estimate of the slope. Here we get 5.06, also greater than the critical value. And so, again, we're going to reject the null hypothesis. And that's consistent with the fact that the p-value is so small. If you want to see a picture of that, this is the picture that sets up our decision rule. Our decision rule was that if our test statistic fell inside this interval, then we would fail to reject the null. But because in both cases our test statistic falls outside that region, in this case to the right, we reject the null hypothesis in both cases. Great. So let's see what's next. Yes, so here we're going to now use the coefficients in this table to write the equation for the line of best fit, and then we're going to interpret what the slopes mean, and we're also going to make a prediction. Right, so the equation for the linear model can be read from this table, and it's simply this: the predicted grade or fitted grade is equal to a constant value plus we have one slope for attendance and we have a second slope for attention. What do these numbers mean? Well, we're not going to interpret the constant or the intercept, but we will interpret the slope. So this number says that the predicted increase in grade for every 1% increase in attendance is 0.54% after accounting for attention. And similarly, the predicted increase in grade for every 1% increase in attention is 0.30% after accounting for attendance. So it's very important when you interpret the modeled slopes, these coefficients, in the multiple regression scenario, you have to say things like this. You have to say this interpretation is what it is after accounting for the other predictor variables in your model. You have to include that. If there's only one predictor in the model, of course, you don't need to do that. But if there's more than one, you need to just be clear that our interpretation of the slope, for example, for attendance, is that the grade will increase by 1% on average. That's the predicted increase on average after accounting for attention. And likewise, when you make the interpretation for attention, you have to say after accounting for attendance. So make sure you include those in your explanations or your interpretations of slopes when you see the multiple regression problem on the final exam. Right, oh, what's next? Now we're going to make a prediction. And so here we're pretending that we have a student who attended 80% of classes, and while they were in class, they paid attention 80% of the time. And so all we need to do is take that model equation, and we're going to substitute for attendance, we're going to substitute 80%, and also for attention, 80%. So it's as simple as this. When we do this calculation, we get 76.37%. And so what that tells us is that the point estimate for the grade of a student who attended 80% of classes and paid attention 80% of the time is 76.37%. Now that estimate, which also appears here as part of my Minitab output, that estimate is a point estimate. And what it doesn't account for is the uncertainty. Also note that this number is our best estimate for both the population mean response when attendance and attention are 80%, as well as the individual response when for that individual they attended 80%, their attendance was 80% and they paid attention 80% of the time. So this same fitted value applies to both scenarios when we're looking at a population mean response and an individual mean response. But what this point estimate cannot tell you is the difference in the uncertainty in those two scenarios. So here we have our 95% confidence interval for the population mean response. So we can say we are 95% confident that the population mean grade when attendance and attention are both 80% is between about 73.34% and 79.39%. By contrast, we are 95% confident that the predicted grade for an individual student who attended 80% of classes and paid attention 80% of the time is between 55.20% and 97.53%. So you can see this interval is much wider. And why is it so much wider? It's because the prediction interval accounts for uncertainty due to individual differences. The confidence interval for a population mean response does not account for those individual differences. And so there's less uncertainty. And the interval is therefore not as wide. Right, so you need to be prepared to explain the difference between the confidence interval and the prediction interval on the final. Oh, great. So now we reach the last question where we're just going to check our model conditions, the linear enough condition, constant variance, and nearly normal. So probably on the final exam, when it comes to a question about conditions, you'll be given a graph that looks something like this one. It's going to have all four of the plots that Minitab outputs. But really, the only two plots that matter are the first ones. So the linear enough condition, here you're going to look at the versus fits plot. And the rule is just this: if the relationship between attendance and grade and between attention and grade these being the two predictors that we included in our model. If they're both linear enough, then the versus fit plot will show no trend. Here, this is clearly the case. There's no trend noticeable in the versus fit plot, in this plot of the residuals. In other words, if you were to fit a linear equation through this data cloud in this versus fit plot, the slope of the line of best fit would be something very close to 0. So this condition is satisfied. The constant variance assumption, you look at the same plot. You look at the versus fits plot. And what you're looking for is to see if the variance of the residuals is the same for all fitted values. If that's the case, then we should see that the spread of the residuals in the versus fit plot is roughly constant. Here, that is the case. You can see the spread is roughly constant. And so therefore, the condition is satisfied. Just to be clear, when the condition isn't satisfied, you're going to see maybe trumpeting. And in that case, it should be very obvious that the condition is not satisfied. Here, we're good. And finally, the nearly normal condition, we look at now the probability plot. And all we need to check to see in that plot, if the residuals are roughly in a straight line, then they are approximately normal in distribution. Here, that is the case, and so the condition is satisfied. So that brings us to the end of our very last skill check. For those of you who've been making use of these skill checks all semester, I appreciate that you're making that effort. I do believe that these skill checks will definitely facilitate your learning process. Hopefully, it made the whole process a lot easier. Having said that, if you have any questions or comments, just leave them in the comments in the YouTube video and I can address them. Or you can also just send me an email or even wait until you see me again next week. We're going to have a meeting next Friday before the exam. I'll send out a notice to all the students to make sure everybody's aware of that. Sometime next week, maybe on Wednesday, I'll do that. Any case, study well, study hard, do your best, and let's see everybody do well on the final exam. Bye-bye. I'll see you later.